Okay, so it's L over 2. In this case, it makes sense that the value is L over 2, because if you look at the wave functions that we come out with, right, or if you imagine a particle moving around in a box, well, the wave function itself is a sine curve, so it's going to look, for n equals 1, something like that. It's symmetric about the middle, and so half the time it's going to be on the left-hand side, half the time it's going to be on the right, and so when we take the average of it, the average is going to be in the middle, right? So it makes sense that the value we get for the average x is equal to L over 2, right dead in the middle. We then looked at x squared, and we found it was a bit more complicated than that. And the reason that x squared is more complicated is because it tends to get weighted more heavily towards the larger values, right, because you're squaring them. When you're doing x squared, it's a similar process. So if you're finding the average of your x squared value, that's equal, if we do it in bracket notation, L, complex conjugate of our wave equation, and then this would be x squared, y of x. So first you would do this part here, which in this case gives you back the exact same thing. It's x squared times your wave function, and so for this one, and then dx, this would be dx, that's equal, integral 0 to L, okay. Then after that, we, well, the reason that we were doing that is because the square, or the variance, which is the square of the standard deviation, all in the x direction, is your x squared minus x average squared, right? And so if we find, we then take the square root of both sides, and that will tell us what the standard deviation is, essentially how spread out your x value is. We did the same thing for the momentum. So to find the average momentum, the way you find a value that has an operator is you plug the operator into your bracket notation or into your integral. So for momentum, that would be psi. Now this is p hat, because that's actually an operator. Psi, and that was from 0 to L, complex conjugate. And then your momentum operator is negative I h bar d dx. So that applied to psi, not star, psi, this is of x dx. So the first thing you have to do is apply these two together. So you would end up taking the derivative of your wave equation and then multiplying it by your wave equation.
Why is it negative this time?
Hmm?
Why is it negative on each
Because that is your momentum operator. I think you're thinking of the Hamiltonian.
Is that always going to be squared? Going to be I instead of negative I? Is there
So-
some out of place where it shows it?
Right. I think you are thinking of h hat, right? Which is h squared over 2m negative d squared dx squared right? This part here, remember this is kinetic energy. This is your energy kinetic term, which is, well, kinetic energy is 1/2 mv squared. mv is your momentum. So you could write this one as momentum squared over 2m. And so if you're applying it in terms of something with an operator, this would be your momentum operator squared, which would be minus I h bar d dx applied to I h bar d dx, which would be, sorry, minus. The two negatives cancel out, so you'd be left with I squared h bar squared d squared dx. So that's your, that would be p squared. You're dividing the whole thing by 2m, so that would be over 2m. Because you have the I squared, that's a -1, and so that's how you get this.
dx squared.
Hmm?
D squared dx squared.
D squared over dx squared, yeah.
At the bottom, last one.
Yeah, oh, x squared, yeah. So because you have the I squared, that's where you get the negative from, okay? But the momentum operator is that's p hat. And if you take p hat sort of times p hat,
And then it goes,
you end up getting this part here. Well, when you divide by 2m, you get this back. Okay.
So p hat equals negative negative I h bar d over dx.
Yes. Okay, so we did that. We came out with, what did it come out with? I think we came out with, no, I don't actually recall. But we then did average of our momentum squared, right? Which, bring it in, psi p hat squared, psi. Okay, so this one was then 0 to L, wave function x, and then you're taking the square of the operator, so it's essentially the operator applied to the operator applied to, well, the function applied to the operator and then applied to the operator again. So because of it's the derivative, taking the derivative of the derivative is essentially the second derivative. And so that would be minus I squared h bar squared d squared dx squared, right? And then psi x dx. This ends up being negative I squared gives you -1. Right, because the negative squared is positive, and then I squared is -1. Right, and then we applied that. We ended up seeing that our momentum, so our standard deviation for momentum was h hat pi n over L. And then the psi we're able to do with that is show, if you take this value times that, you end up with h bar over 2 times, essentially, if we're applying n equals 1, something that's close to 1, right? And so we ended up showing that multiplying that out, you show that for the lowest energy case, or the one where you're going to have the best idea of where stuff is, the uncertainty of the momentum times the uncertainty of the x position gives you h bar over 2, which is what Heisenberg's uncertainty principle said. The key thing that I want you guys to be able to do, though, is if I say I want the average value, know the steps that you got to do. Right? So if I give you the average value and the wave function, be able to come up with that this is L over 2, right? Or be able to come up with what this is. You'll be given, integral tables for anything that's fairly complicated, but integral of sines and cosines, those you should be able to do. Integral of e to the x, you should be able to do.
So basically, we said that equation not going to exist integrated.
Hmm?
If we can't integrate it to the tables.
Yep. If it's anything more complicated than, a fairly simple integral, a lot of the times you'll have a table to go with it, right? But the key is, what's the average value? This is how you find the average value. Okay. So if we, let's see. Ooh, battery's dead. Okay.
What size battery do you need?
AAA. Okay. I think there's a whole bunch in the back though.
Yeah, I think I got some here.
Okay.
Kill.
So what this ends up meaning, if we're starting to plug in different values of n, right? So this p here is your probability distribution function. It's essentially the psi, the absolute values followed by the square, essentially means taking the function times its complex conjugate, right? It's slightly different from an actual squaring because you're applying the complex conjugate, right, to the imaginary value, so you're flipping the sign. It's similar. Thank you. There we go. Brilliant. Thank you. Okay, so the energy values, if you're looking at the difference between the energy states, it follows these patterns where they get further and further apart. This is at n equals 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The wave functions themselves, because you're taking n pi over L times x, right? As n goes up, you're going to get the wavelength decreases, and so you end up with nodes in the middle, and the number of nodes is 1 less than your n value, right? To find the probability distribution function, it's the square of that, and so all your negative values end up getting flipped up, and it ends up sort of compressing your value here, right? So the function looks like that. For n equals 1, the taking psi star times psi, or the complex conjugate times itself, ends up compressing your curve a little bit, making the density more in the middle. Okay. We're going to actually be using this sort of idea, and we're going to maybe do this today to predict the UV vis spectra of conjugated alkenes. Right, we can use this as being our wave function, right? And I think we had the associated energy with it, right, which was right here. This is the energy of each one of your n values. So the L here would be the length. If we're doing a conjugated alkene, then that would be essentially the length of the alkene, or the length of the conjugation. N would be, and as we're going to do it in the lab, is the number of orbitals that are filled with pi electrons, right? And so when you go, we'll demonstrate how we're doing it. It's the number of orbitals that have pi electrons, and then going to the first excited state would be one more than that value. I'll show you when we get to lab. Okay. Before we do that, though, we did Heisenberg's uncertainty principle. Okay, in your homework, you're going to be doing the two-dimensional version. So essentially, it's taking what we just did and adding in there a different dimension to it. Okay, so what it will look like conceptually is your particle is confined along a surface as opposed to a string. And then at the edges of that surface, the boundaries go to infinity. But inside that space, along that surface, the potential is 0. Okay. We will now do. Go. Okay. We're now going to do the 3D box. So as you're working through the 2D box, it's going to be very similar, just slightly less complicated. So it'll be in between the 1 and the 3D box. Okay. So first thing we got to do is write out our boundary conditions, so that as we're going through stuff, we can refer back to them. So our general picture, I'm going to use A, B, and C, but you could use LX, LY, LZ. All right, we're going to make a box. This is your X, that's your Y, that's your Z. The furthest value on the X, we're going to call that A. The furthest value on the Y, we're going to call that B. And then the height is going to be C. So what that means is the box goes from 0 to A along the X, 0 to B along the Y, and 0 to C along the Z axis, right? You could call it LX, LY, LZ, but I have A, B, and C. Okay, so what we're going to say is when it's inside the box, it doesn't feel any force. So our potential, and that's a potential that's in 3 different dimensions, X, Y, and Z, is going to equal 0 for the cases where 0, X is less than or equal to 0, and X is less than or equal to A.
But just to make sure, A is that side?
Okay. I'm just gonna change these. Maybe those will make it a little bit more clear. This is the length in the X direction. This is the length in the Y direction, and that's the length in the Z direction. Is that better? Okay. So L in the X direction. So that means in the slide notes that you have, just cross out the A, B, and C's and put LX, LY, LZ. Okay? So LX is equal to A, LY is equal to B, LZ is equal to C. So 0 less than or equal to Y, less than or equal to LY, 0 less than or equal to Z, less than or equal to LZ. As long as you're within those ranges, there is no potential. B of X, Y, Z, outside that range is infinity. All right, infinite boundary. 0 greater than x, and L x less than x. Right, so if x is outside the parameters, our potential is infinity. 0 less than, or let me make it more clear. X less than 0, or x greater than Lx. Y less than 0, y greater than Ly, and z less than 0, or z greater than Lz. Okay, so those are our boundary conditions. We're going to start with our Schrodinger equation, h hat, psi. But this time, instead of having psi of just the x direction, we got x, y, and z. I'm going to use E total, because we're going to break those up into the x, y, and z direction in just a second. Okay, so as long as we're talking about being inside the box, the Hamiltonian, we're not adding any potential energy to it, right? It's only the kinetic energy in the x, y, and z direction. So this would be minus h bar 2m h bar squared, d squared, no, not d. Sorry. We will be taking the partial derivatives, so del squared partial x squared plus partial, just a little bit more space. I'm going to drop for right now the x, y, and z that goes along with a psi, just for simplicity's sake. Right? So when I have a psi here, that's in the x, y, and z direction. Okay, plus del squared del y of psi plus 1 squared second derivative of psi with respect to z is equal energy total times psi. And this is as long as 0 less than x, less than 0 less than y, y less than or equal to Lx, Ly, Lz. Right? So as long as we're in the box, that's the equation we're going to be using. Okay. We can sort of take this whole jumbly mess and simplify it in writing, sort of simplify it, by using what's called the NAMBLA. It's an upside down delta, right? This means, so it's defined as being the derivative with respect to x plus partial derivative with respect to y plus the partial derivative with respect to z. That's what it means. Okay? And so we could have this as being minus h bar over 2m NAMBLA squared, because we're taking the second derivative of psi. And I'm going to bring back the x, y, and z because I just saved a whole bunch of room by writing NAMBLA. Right, keeping in mind that we're still in that same range. Yeah.
You just missed the, Z, and the, what was it? Like X, Y, Y.
Oh. Bonus point, okay. Okay, so what we're gonna do is we're gonna use the separation of variables technique that we did before, right? On this, right? You can imagine that the wave function, we could think of it as a product of a wave function for the x direction, a wave function for the y direction, and one for the z direction. So I'm gonna call that as being the x function in the x direction times the y function in the y direction times the z function in the z direction. And we're just gonna hope that this works out. This is one of the techniques that you use for these types of equations. You try it because it makes your life a lot easier. Sometimes it doesn't work, which means you just wasted a bit of time, but sometimes it does work, which means you saved yourself a whole heck of a lot of time and effort. Okay?
H bar squared.
Hmm?
Negative H bar squared.
No, this is how I'm redefining the psi. Oh, yes. Bonus point. Okay, Caroline, you gotta correct me. Okay, so our energy total, right, would be then equal to the energy in the x direction plus whatever the energy is in the y direction plus the energy in the z direction. Okay, so writing out this function up top using our separation of variables. I'm going to eventually want to use first board. We would get minus h bar squared over 2m del x squared of function of x with respect to x, y, that's a y, not a psi, y of y, z of z. Plus the partial second derivative y x of x, y of y, z of z, plus partial second derivative with respect to z, x of x, y of y, z of z. And the whole thing is equal to our energy total times the function of x, y, no, it's not. Y of y and z of z. Right, because the x times the y, capital X times capital Y times capital Z, that is our wave equation. Okay?
So you got the long line, the last line you wrote for
Mhm.
the second line, right?
Yep. So essentially I took this line here and replaced psi with x of x, y, y, z of z. So I replaced it here, 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 and there. Okay? Essentially what I'm going to try to do is break this out, treat it as just the x component individually, then the y component, and then the z component to try to detangle everything. That seem okay? Any questions so far? Okay. Now, if you're taking the derivative of this with respect to x, the y term and the z term don't have any x component to them. Right? So if you're taking the partial derivative of a function that's in terms of both the x and the y component, when you're taking the partial derivative with respect to x, y gets treated like a constant. Right? That's how partial derivatives work. Right? So that means that if the y component and the z component are treated as a constant, we can move them outside the derivative.
So whenever you take a partial derivative of a variable, or let's say in that is del squared, del x squared, the only x is a variable, everything else is a constant.
You treat it as a constant when you're doing the derivative.
You treat x, y, z as a constant.
You try y and z as a constant. So if you're taking the derivative of, let's say your function is x times y dx, you treat the y as a constant, so this is the same thing as y d of x dx, or we can do that, right? And so this would be equal to y times 2x. So y ends up getting treated as a constant when you're doing, sorry, this should be partial derivatives. So the more squiggly d you use when you're doing partial derivatives. The way they work in terms of taking a derivative is the exact same thing. It's just when you're doing that, you're treating everything else as a constant. Okay, so this, the y of y is where we're storing all the y information. The z of z is where we're storing all the z information. And so this is, these two, when we're taking the partial with respect to x, is going to be treated as a constant. So we can rewrite this as minus h bar squared over 2m y of y, z of z, that's a z. That is a really ugly. Del squared x squared of our x component, right? Plus, now, for the second one, we're taking the partial derivative with respect to y, which means x and z are going to be constant. And so that would be x of x, z of z, and then partial of your y on its side, partial of y, second derivative, y, del y squared, plus, for the last one, you're taking the partial with respect to z, so the x and the y are being treated as a constant. So x of x, y of y, del squared z of z, del z squared equals e t. Yeah, I don't want to break that out. We got et x of x, y of y, and z of z. Okay. It'd be very convenient to be able to pull everything that has to do with x all by itself, right, and treat it separately. What we're going to do is we're going to divide both sides by the wave equation, right? And by that, I mean we're going to divide everything by x of x times y times z of z, right? So if we divide this whole part by x of x, y of y, and z of z, right? Essentially that whole thing cancels out. And we're going to divide each one of these, well, x of x, y of y, z of z. of x, y of y, z of z, x of x, y of y, and then z of z. Okay. Now we got stuff in the numerator and the denominator, which can cancel each other out. This y cancels out that y, z here cancels out that z, this x cancels out that x, that z cancels out that z. X and y cancel out x and y. So what we're left with is minus h bar squared over 2m, 1 over x of x, del squared x of x, del x squared plus 1 over y of y, del squared y of y, del y squared plus 1 over z of z, del squared z of z, del z squared. Okay, now we have this as being equal to energy total. We already said here that energy total is equal energy of the x plus energy of the y plus energy of the z. This part here times, once we distribute the minus h bar squared over m into each thing, this is your x energy, that's your y energy, that's your z energy. And so we can pull them out and say minus h bar squared over 2m, 1 over x of x, del squared x of x, del x squared is equal to your energy in the x direction. Okay, and we can do the same for y. Y of y, del squared y of y, del y squared equals ey, h bar squared 2m, 1 over z of z, del squared z of z, del z squared equals e of z. Okay, guys good with that? Okay, our boundary conditions for each one of these, we're just looking in the x direction, so we don't actually care so much about where it is in the y and z direction. So the boundary conditions for this are x at 0 is the same thing as x at L of x, and those are both equal to 0, right? Our yeah, because the square of the value, or the square of the wave equation has to be 0 because we can't have, so if it's in the boundary, it can't be there because that's where the potential goes to infinity, right? So we can't actually have the wave equation at the boundary itself. Because the rule for our wave equations is they have to be continuous. And so if as soon as x gets below 0, it's 0, or the probability is 0, then at the boundary it also has to be 0 so that we have a continuous function. Okay, so the restriction of continuity means that at the two boundaries, our value for the wave equation, right? Capital X is the X component of the wave equation. So, the values for X at 0 and X at our boundary have to be equal to 0. The same thing applies for our Y's. Y of 0 is also the same thing as Y at L of Y at 0, and then Z is equal to Z L Z equals 0. Okay, now if you look back at your notes, when we were doing the one-dimensional particle in a box, that's what it looked like, right? Because we've broken this up into individual components, and each component looks like the one-dimensional particle in a box, the solutions are gonna be the same as the one-dimensional particle in a box. Right? So this looks like the one-dimensional particle in a box, and so you're gonna get the same answer. So that tells us that our X of X for a given n value will be equal to A in the X direction sine of the quantum number, or n, in the X direction, pi over Lx times X. Our Y value, so this should be n sub X, that's n sub Y, in the Y direction. And our Z and Z equals A in the Z direction, sine and Z I over L Z, Z. And this is 4 and 4. And X equaling 1, 2, 3, dot, dot, dot. And Y equaling 1, 2, 3, dot, dot, and Z equaling 1, 2, 3, so forth. Okay.
What's the A exactly?
Hmm?
A?
A is going to be the normalization constant, which we're about to do. So A is the amplitude, or the height of the, for a 1D particle box, it's the height of the sine function. When you're doing, one of the properties of a probability distribution function, or our wave equation, is that the integral from your lowest value to your highest value of psi star psi d, and then whatever you're working with. So if we're just looking at the X direction, that has to equal 1, right? Because the complex conjugate times itself, that is the probability distribution function. And part of the things about probability distribution functions is if you take the integral over all possible values, it adds up to 100%, right? So what these A values are, AX, AY, and AZ, these are the normalization constants, so that when we take the integral over all space, we end up with, 1. Okay, so that's the purpose of AX, AY, AZ. So, our, if we bring everything back together for our original wave equation in the x, y, z direction is x times y times z. So that would be equal ax sine of nx pi lx x times ay sine ny I, bless you, y y z sine of n z I over L z z. We can bring all of our a's together, so this is a x, a y, a z. Right, this here is our n value, or our normalization constant. Okay, so when we're dealing with a one-dimensional particle in a box, the a value was equal to the square root of 2 over the length of our box, so in this case it would be Lx. The exact same thing for this one, right? If we normalize this one individually, this will give a 1 times 1 times 1. So if we, what we need is the normalization constant for each one of these, because each one individually can be thought of as a particle in a 1D box. The normalization constant for each is going to be the same as we had for the particle in a 1D box.
Wait, so what was the L over Q? That was probability?
Hmm?
Remember we also had like L over 2?
Oh, the L over 2 was the average value of x. Yeah. But before we can do the average value of x, we need to know the normalization constant. So when you're finding the average value of x, 0 to L, the wave functions that you're using are the normalized wave functions. And so you need to know what the normalization constant is, so you can be applying, star x psi dx. These two, those functions had to be normalized. And so we need a normalization constant, and it's 2 over the length, the square root of 2 over the length for the 1D particle in a box. And because each one of these individually works out, when you look at each line, is the same equation that we had for a one-dimensional particle in a box, you can go back through your notes and you'll get the exact same value for each one of your dimensions. Okay? So, if that is your normalization constant, that is going to be equal to the square root of 2 over Lx, square root of 2 over Ly, root 2 over Lz. Put them all together, and you get the square root of 8 over Lx times Ly times Lz. So, our wave equation would then be square root of 8 over Lx, Ly, Lz times the sine and x pi Lx x And that's for nx being 1, 2, 3, and y being 1, 2, 3, and z being 1, 2, 3. They have to be integer values. Okay, so if we take, plug this through our, so we take the second derivative of our wave equation with respect to x, y, and z, and then have our, what is it, minus h bar squared over 2m, right? This here is our h hat, right? We apply that out, taking the second derivative of each one of these with respect to the x value, y value, z value, individually. While you're taking the derivative of this thing here with respect to the x, these two are treated as a constant. While you're taking the derivative of this whole thing, second derivative with respect to y, the x and the z component are treated as constant, and then the z, the x and y are treated as constant. Okay, what you'll end up with is that this is equal to h bar squared over 8m n x squared over l x squared plus n squared y over l y squared plus n z squared over l z squared.
That's, we're gonna do that by the tables.
Hmm?
We're gonna get the answer on the tables, right?
Oh, you don't need an integral table for that. No, well, you wouldn't need an integral table because you're taking the derivative, but if you're taking the derivative of this whole thing, first with respect to x, right, these two are treated as a constant, so that would be sine n pi ly over y, these two in front. Taking the second derivative of this gets you back that same function with a negative sign in front of it, right? And then times n pi over x, that should not be there,
It's h squared.
h squared. Okay, if we take the second derivative, are you okay if I do one of them, and then you can sort of see how all three of them apply together?
So what are the sign for?
Hmm?
What are they signed at?
Okay.
I'm gonna sign.
We'll get there, okay? So, this is essentially the sum of each one of our three derivatives. Right, this is the result from one of your derivatives, this is the result from another derivative. So this is the result from derivative of your wave equation with respect to x. That's the from the derivative with respect to y, second derivative with respect to z. Okay, so if we do just the x and show you that that one works out to be that, then you repeat the same thing for y. Okay, so if I take this whole thing is a constant, right? And once you define your box, 8 over the length of the x, y, and z, that's a constant. So I'm going to take the derivative of this whole thing with respect to x. This is a constant, and these two are constant, so I can pull them out. So essentially I'd have the square root of 8 over Lx, Ly, Lz times sine n y I over Ly times y. Sine n z I derivative of the x component, sine nx pi l x x. Thinking the second derivative of that with respect to x, right? All the rest of this stuff is a constant, so I can shovel it off to the left in front of the derivative sign. Okay, if I take the derivative of sine, what's the derivative of sine? Right, it's cosine. So this would be equal to, you take what's in here, so that'd be n x pi l x cosine of n x pi over l x x. Right, so that's the first derivative. If I take the derivative of cosine, I get negative sine. So this is first derivative. The second derivative would be taking the derivative of sine of ax is, taking the derivative of cosine of ax is minus a sine x. So we would get nx squared pi squared over l x squared. And then times the negative sine of n x pi l x x.
With you so far.
Guys all good with that? Okay, so if I plug this back in over with here,
Could you play with the second one first and see how that plays out?
the second one.
So like second line you have down there, last one, there you go, that one. Where you have on the right, you said we're gonna do this, and we did that on the side.
Oh, okay, yeah. So what I'd be left with, and this is for the derivative in the x direction, so doing just one of them, this would be the negative root 8 over L x Ly Lz. And then I'm going to take this constant, move it out front, n x squared pi squared L x squared. So I took the negative here. One of the steps I did is I took the negative and put it out front already. So that's where this negative came from, right, is from the sine. So what I'm left with is sine n x pi over L x x sine n x pi, nope, y, and y pi L y y sine n z pi L z z. Okay, this part inclusive. No. I move these two, switch locations of them. All right. And x squared pi squared over L x squared, and then square root of 8 L x L y L z. This whole thing here, I got back my sign, that is my wave equation from up here.
psi of x, y, and z.
Yeah, this is, what's here is psi x, y, z. Having taken the derivative of just the x direction. So from the x direction, I get a negative here, nx pi squared lx squared. If I take that, so if I do the same in the y and the z direction, I'm going to get the exact same thing for the y and the z direction. If you look back through your notes, yeah, right here. We were essentially taking our function, the second derivative in the x direction, plus second derivative in the y direction, plus second derivative in the z direction. So if I'm doing that down here, this is the result for the x direction. For the y direction, I'll get the exact same thing, except this will be ny and ly. And then in the z direction, it would be nz and lz. Right, because when I took the derivative of the sign here, that was derivative of this with respect to x. The x component, the y component, and the z component all look the same. The only difference is that it's wherever you have an x, it becomes a y, wherever a y, it becomes a z.
So where did all the pies go?
We're going to get there.
Oh.
Okay. So what we would have is minus h bar squared over 2m, okay, times all that junk that we just did, which would be essentially minus nx squared pi squared lx squared, and we get back our wave equation in the x, y, z direction, plus u, plus negative n y squared pi squared ly squared, back our wave equation in the x, y, z direction, plus negative nz squared pi squared lz squared. The long wave equation in the x, y, z direction. Okay, so you see that I have the wave equation, psi, in all three. I can pull that out. And then what I'm going to do is I'm going to take my h bar there, and I'm going to turn it back into the h over 2 pi so you can see where the pi's get canceled out. Okay, so this is minus h over 2 pi squared over 2m minus nx squared pi squared lx squared plus negative n y squared pi squared ly squared plus negative n z squared pi squared lz squared psi x comma y comma z. Okay. Here I have pi in the denominator. Here it's in the numerator. This is h, essentially h squared over 2 pi squared. And so this pi here is going to cancel out each one of those. So I have h over 2 squared. H over 2 squared is h over 4, and the so that would be h over 4 times 2m, or 8m. We got a negative here, and we got a negative in front of each one of those. And so the negatives cancel each other out because they're being multiplied together. This negative cancels out each one of those. So that's h squared, and then n x squared over L x squared. And y squared, ly squared, and z squared over L z squared. So 4 times 2, that's 8. Okay, and that would be right here.
So pi's cancel each other out.
The pi cancels the pi that we had here, the pi squared, cancels out the pi that's embedded in the h bar. Okay, so why this is important? Let's say that our box has the exact same dimensions, right? So the Lx, Ly, and Lz are the same. So if we let
Series I, X, Y, Z. Yeah.
Lx equal Ly equal Lz. So it's a, true cube. Okay? So we could actually bring these then together, because if Lx, Ly, and Lz are the exact same thing, then this would be h squared over 8m. Each one of these would be divided by the same value until we can bring them together. And we're going to say, we're just going to call this L. And x squared plus ny squared plus nz squared all over L squared. Okay, so this is our energy total. So, what happens, let's make a little bit of a column, like n x, n y, and n z values. Let's say that these are all 1, right? You're going to end up with some energy. Let's say we make one of them 2 and the other 2 1. So we could have 2 1 1, or we could have 1 2 1, or we could have 1 1 2. Well, if we look at the numerator here, so the numerator, right? 1 squared plus 1 squared plus 1 squared would be 1. 2 squared.
Wait, what?
Oh, sorry. Yes, it would be 3. The next one would be 2 squared plus 1 squared plus 1 squared, right? That would be 4. 6. Okay. 1 squared is 1, plus 2 squared is 4, plus another 1 squared gives you also 6. And then this other one also gives you a 6, right? So there are 3 different states that give you a value of 6. What that is called is degeneracy, right? All 3 of those states are degenerate. They have the same amount of energy. So that's where degeneracy comes from, right? If you remember back from general chemistry where the px, py, pz are all the same value, it's because they're degenerate.
Can n, like as we said, can n be like 3 and above, right?
Yep. There's probably a certain combinations that have more degeneracy than just 3 different states that are the same. If you carefully select your n values such that the square is like the square of something else, or something.
So what's the dividing by L squared deal?
Well, if the L squared is the same value each time, then it's 3 over L squared, 6 over L squared, 6 over L squared, 6 over L squared. As long as you're dividing by the same value, you're going to get the same energy. What differentiates the energy is as long as we're staying in the same box, is your different quantized value, your different n values. Those will give you different energy values, right? The H is a constant, your mass is gonna be a constant. It's gonna be an electron most of the time. The L is the length of the box, and if you're talking about a cube, then what gives you the different energy levels is your different n values. Okay,
But if L is not,
if L's not, then they could be degenerate, but only if you have very specific combinations of L.
so
Makes
would-
So most of the rest of the time, they're not gonna be degenerate.
should we be worried about just a cube?
No, this is sort of the explanation for why things end up being degenerate. So when you're doing your particle on a plane, you'll have also degeneracy, because essentially your answer is gonna be the same thing except without the z term, right? You'll come up with so the entire solution here for the three-dimensional particle in an actual box is the same thing as a particle on a string in three directions, in three dimensions. That was the end result that we got. So for yours, you're gonna get the same answer except just on two planes. So essentially, as you're doing the whole thing, just drop out the z.
That's what we're gonna get to.
Yeah.
It's gonna be h squared or 4m.
Well, yeah, it'll be 4m as opposed to 8m, but yeah.
So if you had, let's say, n equals 3, right? So basically, as you increase the n levels, there's less chance of having degeneracy.
No, as you increase the n levels, there's actually more chance for degeneracy.
Well, it could have like less. Really? Because let's say if it has like 1, 2, and 3, right? Then it could also have like 1, 1, and 1. It could also have 1, 1, and 2. So it's like it's kind of.
A lot of times you're gonna have a degeneracy of 3, right? But there are other, there's other ways of combining it. The key point that I want you to take home is degeneracy comes about from certain combinations of your n values. And it comes about when you're talking about more than just particle in a 1D box, particle in a plane where the length of the y and the z, or sorry, the length of the x and the z are the same length. You can get degeneracy for that one as well. Okay, does everyone have this written down? Yes?
On paper.
Okay.
So that was particle in 3D.
Particle 3D.
So I thought the 1D1 was h bar squared over 2m. Like that's what I've written down.
That's what h bar over 2m is. And h bar over, not h bar, say squared. That was the mistake. Or that was the correction.
And then n squared, I squared over l.
That's 1. You have another will be h squared over 4m, n squared is n, y squared over l squared. If you have 3, that's 3 right here. So it is h squared, right? Not h bar squared?
Hmm?
So it is h squared, it's not h bar squared?
Yeah, H.
Okay, yeah.
Yeah. Okay, so here's example of degeneracy. Combination where you can have 6. Right? 3, 1, 2, you could have 3, 1, 2, 3, 1, 2, 2, 3, 1, 1, 2, 3, 1, 3, 2. So in this case, there's 6 degenerate states.
Then it goes right back to being 3. So,
Hmm?
then it goes right back to being 3 if it had like 4.
Yeah.
There's still 5. It's not like increasing as you increase n.
No.
That's what I was right.
If they're all the same, like 2, 2, 2, there's only one way to write that.
Yeah.
If 2 of them are the same, there's 3 different ways of writing it. If all 3 are different, then there's 6 ways of writing it. So I guess the max degeneracy you're going to have is 6. Although you could, in theory, have combinations that get you the same sum of the squares, although none come to mind easily. I think you'd have to have really high n values for that to start being a case. Like if n was 8, then you could have a 2 and a 2, and those would come out to 2 squared. Well, no. You'd have to have certain values. Okay. So, yeah, we're gonna take a break.